Hello, my name is Estella, and today we will be doing part B of homework 1. We're going to look at a problem involving a series of two gravity drain tanks, and we're going to look at it with a proportional integral controller to manipulate the height of the second tank. I will also be using the Fundamental Theorem of Calculus to change our integral term into a state variable. And then finally, we're going to code this all into Colab to actually solve our initial value problem with our dynamical material balances. And we will see what the response is when we change our height set point. All right, now to start with this problem, we can start off by drawing out our two tanks. They will both have a liquid level, which we will define as H1 and H2. They will have flow rates coming in and out, which we'll define as Q in, going into the first tank here, Q1 going into the second tank and out of the first tank, and then Q2 leaving the second tank. They also will both have equal cross-sectional areas, which we will define as A, and equal cross-sectional areas of their drainage holes, which we will define as AH. And so from part A of this problem, we came up with the dynamical material balances. And so I will rewrite those right here. We had the change in height 1 with respect to time being equal to 1 over the cross-sectional area times Q in minus Q1, and then we found that Q1 is equal to the cross-sectional area of the drainage hole times the square root of 2GH1. Then we also found that second one, which is the height, or the change in the height of the second tank with respect to time equal 1 over same cross-sectional area times Q1 minus Q2, with Q2 being equal to AH times the square root of 2GH2. So these are the two dynamical material balances for these two tanks right here. And so with the use of our proportional only controller, we defined our flow rate in to be equal to Q in naught, what we set the rate as, plus Kc times our error, which we defined as the set point height minus H2, the height of the tank liquid level that we are trying to control. So this is what we defined as our Q coming in. And so if you noticed from our last video, part A of this problem, with our proportional only controller, we never quite reached that height set point that we were aiming to reach. It got closer and closer, but there's still a lot of error. We couldn't quite get it to that value that we wanted. So we are going to be adding in a proportional integral controller. And so what this will do is this will help offset some of that error from the proportional only controller. So what that looks like here is we're going to call our proportional integral controller Ki. I'll write that here. And that's going to be multiplied by the integral from 0 to t for time of that error, hsp minus h2. This is going to be with respect to tau, our axis of time. So this integral here kind of makes things a little difficult. And so to simplify it, to make it easier so we don't have to solve this difficult integral, I'll be using the Fundamental Theorem of Calculus that states that if you take the derivative of an integral, it is the integrand. So what we're going to do is we're going to have a new variable that we're going to define this integral as. We're going to call that E int for the error for our integral controller. And that is going to be equal to this integral. I'll rewrite that here. And so if we take the derivative of both sides with respect to time, we end up getting the derivative of e int over dt. And then the derivative of this, we end up getting this integrand here, that hsp minus the height of the second tank. So we're going to use this to redefine this so we don't have that integral in there. So we can actually rewrite this Qn equation right here. So Qn is going to be equal to Qn naught plus our proportional only controller times error plus Ki times E int. So this is going to be our Qn value, the value that is constantly changing to get us closer and closer to that height set point. And so we can now rewrite our equation over here and sub in this for Qn over here. So I will rewrite that here. We have a change in height 1 with respect to time equal to 1 over a, and then our Qn, which is Qn naught plus kc times e plus ki times e int. And then that is going to be minus Q1. And so this is what we end up getting for the change in height 1 with respect to time. And I will also just write our second one here as well, the change in height 2 with respect to time. It'll be the same. It'll be 1 over a times Q1 minus Q2. And so these are actually the three equations right here that we will need to solve this. And so now we can put these into Colab and manipulate the proportional integral controller and see how the system changes when we set a new height set point.
So now we are going to move on to the coding part of this problem. I have the solution right behind me still, but I did copy and paste our problem statement right here just so that we have it, as well as same as the last part. I imported a few libraries so that we can access functions such as square rooting, solve IVP, and also plotly so that we can actually plot our solutions. We're going to use the same values for our variables here as we did last time. So I have defined those there. And then next we are going to define h naught as, and we solved for this in the last video in part A, is Qn naught divided by h squared divided by 2 times g. And then next we want to define our set point as 1.2 times h naught, because we want to see what happens when we set the set point at 20% higher than the initial steady state. And then we have our proportional only controller, which is going to be just a random value, kind of same as last time. We're going to do 0.1. And then here is where we actually put in our PI controller. We're going to define that as Ki, and same as our proportional only controller, we're going to define that as just a random value right now because we don't know what works for our system yet. So I'm going to set it as 0.01 right now, and we are going to come back to it and see how it changes our system and see how it plays in a role in the heights of our takes and how fast we can get to our set point height. So now let's define our key end, the time we want our simulation to run for. We're going to set it at 1,000 seconds. And then we want to define our t-plot to equal numpy.length space 0, the end 1000, kind of the same as last time. And I'm going to go ahead and return our H0 and HSP values just so that we have those there. So the initial height of our tank is going to be 5.1, and the height we want to reach is going to be 6.12. So next, we can go ahead and start, we can define our right-hand side here. So define right-hand side, we're going to use the same variables as in part A, t for time and vec for vector. And we're going to define h1, h2, and eint, our new error, as vec, so that we can see how those all change over time. And then we're going to define our flow rates. And then in the last video, I created a variable alpha just to make it a little simpler typing these. So I'm going to do that again. I'm just going to put that up here. Alpha equals, and that's going to be AH times the square root 2 times G. Right. And then we can put that down here. So the flow rate 1 is going to be equal to alpha times the square root, pi dot the square root of h1. And then similarly, q2 is going to be equal to alpha times the square root of h2. All right. And we also want to define our error down here as well, equal to hf minus h2. And then we want to define qn, which is going to be equal to qn naught plus that proportional only controller times the error plus our new pi controller, ki, times eint. Right, that looks good. And then we want to return our qn minus q1 over a, q1 minus q2 over a, and then we also want to return our error. All right, so that all looks good. So now we want it to actually solve our initial value problem. So we're going to do our results equal to solve IVP. We want it to solve our right-hand side, 0 to the end there. And we want to define our starting values here. We want both of the heights of the tanks to start at h0, and then we want our error to start at 0. We want our method to be redo and dense underscore output equal true. Oh, okay. And then we want to define our plots here, h1 plot, h2 plot, and eint to equal res.solve and then tplot. Right, shift enter. Now we want to actually add our plots. So we're going to do fig equals make subplots. We're going to do fig.add scatter. And we're going to do x equals tplot for time, y equals h1 plot, and then we want the mode to be lines and the name to be h1. Okay, I'm going to copy and paste that for h2. So then we want to update our layout here just to make it look a little better. So we're going to do fig.update underscore layout. We're going to set our width equal to 600, height equal to 400, and then we are going to set our template to be equal to plotly underscore dark. Okay. All right. So no errors there. As you can see, our liquid levels of H1 and H2 are plotted right here, and it actually is hitting our set point. So that PI controller helps to offset that error from our proportional only controller, and we reach our set point a lot faster. So let's mess around with these values up here and kind of see how it impacts our system. Let's maybe try and increase our PI controller a bit. Let's make it 0.05. Okay, so this is kind of what we saw in part A when we increased our proportional only controller a bit too much. The heights actually would diverge and the system would become unstable. So you can see how powerful this PI controller is because I increased it by 0.04 and it already diverged. For our proportional only controller, we had to increase it to, I think it was maybe 1 or above 1 for it to diverge. So you can see how powerful this is. Let's take it down a bit, 0.02. So it definitely increases our oscillations here, but we're still reaching our set point. So it looks good, but let's go back. Looks like maybe 0.1 was really good there. Yeah, we only had like 2 oscillations here. Let's maybe decrease it and see what happens. I'll go maybe 0.005. So barely any oscillations there, and we still get to our set point pretty quickly. That looks like it's pretty good value. Maybe let's do 0.055. Yeah, that looks very good. So what happens if we increase our proportional only controller while we have this other PI controller here? Maybe let's change it to 0.02. So yeah, it increased our oscillations there. The frequency of them, or the oscillations are happening very early on, so it's still not even like as bad as it was with just the proportional only controller. See what happens if we make this 1. Let's just see what happens there. Yeah, so all of the oscillations happen very early on, and we still will eventually reach our set point, it looks like. So you see, there is a certain combination of our proportional only controller and our PI controller that work together. So it looks like a good combination is what we had, 0.01 and maybe 0.055 or 0.06. Yeah, that looks very good. So now that we have kind of established our controller values there, let's see what happens when we change our set point height. So we have it as 20% higher than that initial steady state. Let's maybe make it 100% higher. Put it at 2. So definitely increases that oscillation there. And our new set point, we have it returning here, is 10.2. So it still reaches that value. Let's try and get as little oscillations as possible. We will need a new value down here, say 0.01. Definitely increase those oscillations there. So it looks like we actually have to decrease this from what we had before. I'll do 0.003. Okay, so it's very gradual here, so it looks like that's too low, 0.005. So very little oscillation, and we still reach our set point. Maybe do 0.046. Yeah, so barely any oscillation there, and we still get to our set point relatively fast. So looks pretty good, I would say. Thank you for watching this video.